Hi everyone, this is David Ngo. Today I want to share with you another new topic I call derivative. Called derivative. We probably, if you study in high school in the past, you should know derivative. But anyway, this one I go through all the detail. So just review it, right? Review or revise it. Where do derivative formula come from? There's a clear intuitive guide for a beginner, right? But the big idea behind the derivatives, every student encountered this table of derivative formula at some point. You remember x to the power of x, derivative will end at x to the power of n minus 1. For function e to the power of x, then the derivative will be the same. For log x, then derivative 1 on x. For sine x, derivative is cos x. Cos x, the derivative is minus sine x. Tan x divided with sec square x. That's we you to remember it by heart. But anyway, today we're gonna find out where they come from. So this someone just make all this stuff now. Every single formula will derive from one fundamental question. The core question is if I nudge the input by a tiny amount, how much does the output change? Right? When you change a little bit the tiny amount, so what does the output will change? Now, changing input, check what's the change in the output. This idea is captured by the formal definition of the derivative. This is derivative of function x, otherwise written m. That the first derivative of function x is the limit of this function x, a little change in x, or plus a little bit more here, add x in here, and take away the function of f. That means you increase a small amount. Right, when hex move to a to zero, when hex move to very small amount, right? Not to zero, but not equal zero, right? If it's equal zero, not working, right? It's very close, very tiny bit. So we see if a hex move to the tiny bit, then what will happen? So in blending derivative, the tiny change in output divided by tiny change in input, we shrink the step size hex down towards zero to find the intended drag of the change at any point. This I remember, this is the formal definition, right? To understand how derivative work. Right, we go to one by one, so you see it quite clear. Remember the formula, right? We will increase the input by a little bit, see what the output will look like, okay? All right. Where is formula come from? Let's work through its common derivative, building the intuition from scratch, right? Example, why the x squared become 2x when you take the derivative, will become 2x. Start by just looking at what the function does. Like a function x, if it, x and x squared, so x equal 1, 2, 3, 4, 5, 6, x squared will be 1, 4, 9, 16, 25, right? We all know that. So the change in output in this case, 1, 1, no change. This one change the output, right? From 1 to 4, that means plus 3. From 1 to 9, from 4 to 5, to 9, we increase by 5. You see that? So this is changing output. When you input 5, they come up increase by 9. You see that? The change is in 9. All right. This explains very clear. When you put x equal 5 and x squared will 25, right? But changing output from 4 to 5 to a little bit here will be 9, right? Right. You see that little change? Right. Each time x increase by 1, the output grow by an odd number, 3, 5, 7, 9, and you can see it very clear. That pattern increase by 2 each time, right? It's no coincidence, but in 2, different 2, different 2, different 2. Now apply the definition formula, we replace fx x squared. So the derivative of function x or limited x when we plus x little bit here, square minus x squared, you know, the function f x squared here, right? So we will replace a little x in there. So when x move to approaching to zero or approaching a tiny bit. So we're expanding this one here, we expand the function here. You know that this is going to have to expand it. The x term will cancel because it minus x term. So what left over here? The derivative of x leave there are 2x hex, right? The left 2x hex per hex squared or divided by hex. So you divide so you got the limit of 2x per hex equal 2x. But when hex becomes very small, so the limitation it end up equal 2x, right? Because this is little small, so 2x. So that's it mean the result is when I hex go to very small to 0, then the x disappear and we get f first derivative of x equal to 8. At x equal 3, the slope is 6. Right? If x equal 5, the slope be 10. So the bigger the x is, the stiffer the curve. See, that's what explain where the x squared derivative of x squared become 2x. Okay, that's a simple one. Next one. Why the EX stay EX? This is the number E, that 2.719 is special, the special number. It is defined to be unique number whose exponential function grow at a rate exactly equal to its own current value. So that's our circular. But here, what does mean in practice, right? Current value of e to power 1 equal e, right? E to power 1 to power 5, 20, you take one kind of roll right in that point will be exactly the same. Right? Use your calculator, you work it out. So roll right at the point. No other byte has this property. This is very special. For example, 2 to the power of x grows slower than itself. 3 to the power of x grows faster. Only e to the x hit a perfect balance. That means exactly the same. So result because ax is defined so that its growth right always equal itself. So that our first derivative will be equal itself. But a special ax, remember a 2.719. In fact, it's a long number, but it's only simplified to 3 decimal place. Okay. Example 3. Why does sine x become cosine x? Right? The sine becomes cosine. Use this for how about example? Give you the Ferret wheel that the white side x how they work out. If it's circular here, this by the x is the angle x. This one is the phi a. This line is sine, and this one is cos x. So the length of the cos x here. So velocity whenever cos x equal up here, cos x is here. Then sorry, this is the sine, and this is the cosine. They are always on opposite one. When you lower the one higher, the one higher, the one lower. So let me explain. Imagine a Ferris wheel rotating at a steady pace, right? Your height above the ground follow a sine way over time. Sine x tell you your height at any moment. Decide your height at any moment. It is sine x here. Cos x tell you how quickly your height is changing at that moment. Right? Cos x at that moment. When you are at the very top, I mean sine x here. Sine x equal 1. At the very top here, sine equal 1. Your height is momentarily not changing, so cos x equals 0 here. Cos x will be equal 0 here. Right? That when you cross the middle going upward, your height changes faster. And in that cos x will equal 1 at that point. When your height and cos equal 1. We're changing very low one equal 1. This can be verified using the limit definition and the two fundamental geometry limit covered in the part 3. We'll talk about that. The derivative of sine x is the limit of sine when plus little small heck here, right? Minus sine x divided by x to end up cos x. Right? So in truth, the cosine is the velocity of sine. Where sine rises fast, cosine is large. Where sine peaks and pauses, cosine is 0. Right? That's why we remember when we take the risk, sine x become cosine x, right? That's explanation. This one was very clear for you, right? So see what you look at your sine x at high vertical position, sine at high vertical position, cos x at a horizontal position here, right? It's the angle x here, right? So that's this one is to explain what you got is sine x. If you remember, if you learn it is a triangle, and it's the right triangle here. Sine equal opposite divided by diagonal. Cosine equal adjacent divided by diagonal. It's remember it when we learn about our geometry, right? So at the angle x, you can see sine x is a high, and cos x is a horizontal. This is the high and the horizontal. So the radius in we just said is 1 for simplicity. That's all. Because radius is 1, where the side, the high and horizontal position are exactly sine x and cosine x. Okay, all the pi that mean 90, right? Pi on 2 that mean 90 degree. This is 0 degree or 360 degree, 2 pi 360. So all the position, look at our position on the wheel. You know, when you look at position, when you move, position, you got this is first one will move 90 degree, right? So starting with 0 degrees, start with 0, then you go 90 degree. You got this is pi 180, this is 270, and this is 360. So that's the way you run around the whole circle. So look at the side, how the y is equal sine x, and this y, this different color is cos x, right? You see the sine x running here, the sine x running on this curve, and cos here. Cos x just on the opposite one, just opposite one, right? Cos x running like that. So that's why. So cosine is how far left or right you are. Where sine rises fastest, cosine is largest. Right? Where sine is 0, right? At the side, cosine equal plus minus 1. See that was when you go to 0, go plus or minus 1, right? Where sine is higher or lower, top or bottom. Okay. So why the cos become minus sine? If we talk about sine, derivative of sine x cos. Now we'll take derivative of cos x. Why become minus sine x? Back on the Ferris wheel. Now track your horizontal position instead of your height. That follow cosine, right? Here the key inside about a negative sign. When cosine is at its peak, x equals 0, it's about to decrease. So the rate of change is negative. So you imagine when you're going down where cosine is at peak. When cosine is falling faster, sine is at peak. So the magnitude matches. So they're opposite, right? Result. Let me derivative cosine equal minus sine x. The negative side tells us the direction of change, reverse compared to sine. If you look at the look back to the wheel, then you can see that, right? Why does the log x become 1 on x? We said if the natural logarithm, that means the big log x, not the this called natural logarithm, grow quickly at first, then slow down dramatically. Like x equal 1, log x equals 0. But change in log x, nothing here, undefined. 2, log x2, you can check it using calculator, you work it out. You see change in log x from 0 go to 0.693, then from 0 to 1.6, the change is 1.610, right? And this is see to get the changing here. That means this one take away, I give you it. All right, you said the difference of the two number here, the difference of the two number give you this number, the difference of two number give this number. Okay, so the rho in log x keep halving rapidly at x rho tenfold. When x rho tenfold, see that that's the change at 1 point something. But when x rho the thousandfold, change over really, different from 100 to 1,000, not much change, is there? For x from value 100 and 1,000, see the change very, very minimal. So you can see that so the row x keep having roughly x row tenfold. It perfectly matching the formula 1 on x. When x equal 1, the slope is 1 on 1, state very simple. When x equal 10, the slope is 1 on 10, 0.1. But x equal 1,000, the slope is very, very small, almost flat. So result are derivative of log x equal 1 on x. The larger x become, the flatter the curve. And 1 on x is capture exactly how fast the flattening happening. So that's why log x become 1 on x. The three fundamental limits we talk about are the derivative formulas for sine x, cosine x, and e to the power x, or called exponential and exponential x, right? All rest on three specific limit results. They are arbitrary. They describe what happens when a tiny step h shrinks towards 0. Think of h as a microscopic footstep. I gets infinitely small. Certain expressions settle toward a fixed value. Here, this one explains the limited sign h on h equal 1. This might seem surprising. Isn't sin h always smaller than h? Say yes, but only slightly. For very small h, a h shrinks. Sin h and h become nearly identical. Look at h is equal to 0.1. Sin h gives you this number, and of course you this one divided 0.1 give you this result. All right, same like when I was thinking when h very small 0.001, then sin h become this number here. you side divide by heck, you got this 0.999, right? So almost equal 1 anyway, isn't it? 0.1, so they equal, this is equal to 1, almost 1. That's why I said the limit to sine heck over heck equal 1. So the ratio much closer and closer to exactly 1. So plain English, for tiny angles, sine is almost indistinguishable from the angle itself. The arc and the straight line nearly coincide, right? They are coincide. So that's why I see that we remember we learned it once. So limit of sine hex over hex equal 1. Now the limit 2, got limit cos hex minus 1 or hex equals 0. This one is well, this one was when hex is tiny, cos hex is extremely closer to 1. Right? We learned it before. Cos 0 equal 1. Right? So this one. So cos hex minus 1 is an incredibly small negative number. Okay, because it's nearly to 1. So something nearly to 1, take away 1, so with very small numbers, incredibly small negative. This will be negative because cos is less than or equal 1, right? Maximum is 1, so this one less than 1. Look at our figure here. Hex is a variable. I'll give you all now. Cos hex will be this. And cos hex minus cos take cos hex minus 1 divided by hex give you this answer. So you go to when hex increase, go down to decrease to 0.0.1. Cosine hex will give you the number, right? Then you go see it, they want 0 almost equal to 0 with so many variables. So the smaller the hex, closer to 0 it become. Right? The smaller the hex, the closer to 0 it become, right? So the numerator shrink much faster than the denominator. So the whole fraction collapses to 0, right? So plainly, for tiny angle, cosine barely move away from 1. The change is so small that divided by hex still give 0. Okay. So limit 3, talk about e to the power hex, exponential hex, right? E to the power minus 1 divided by hex equal 1. This limit is what define a special. Let's see the number. Hex upon your e to the power hex give you 1.105. So the put in formula, let's see that result here. So when I hex more reduce to 0.0001 here, and e hex still 1, that's a very change 1 point something. When you divide it, exactly got 1.001, almost 1. Anyway, that will end up to 1. So the smaller this one, then you go closer. The ratio approaches 1 perfectly. No other base does this. Right? For the 2 to the power hex, you will get 0.693. For 3 to the power hex, you will get 1.0999. Right? So that's different. So only the one perfectly matching it. So plain English, the number A is defined so that its tiny growth rate is exactly 1, marking AX is a perfect natural exponential. That's why we call them a natural exponential. Okay, part 4, we're putting it all together. Now we can see how the three limits fit into the derivative formula. Here is the chain, right? Derivative of sine x, step by step, we start from the definition of the derivative, like the derivative of sine x, the limit of hex of sine x plus little hex here, minus sine x divided by hex. So when you use the angle definite identifier, we explain the sine x plus hex was give us the formula here. If you remember this in classical science, expand give you this, right? We always learn by heart when we in school, right? Substitute it into the derivative formula. Substitute this one here into the derivative. Got limitation of when you time it one give you the information plus the 1 minus sine x, right? Substitute it. So the limit is x here. We'll substitute in there. This one keep it. We'll take sine x common out. So you give you the one side cos plus cos x times side. That become two derivative here. What we try to do, two limit here. Right, so now we use the first limit, this group here, limit cos x minus 1 on x, and limit sine of x. So this one approaching to 0, this one approaching to 1. So this the function becomes sine x times 0, cos x times 1, so equal cos x. So that's the way we prove it. Right? Therefore, the derivative of sine x equal cos x. That's the way we prove it. Right? We prove where this derivative coming from. Right? When we look at the ferret wheel, we just talk about the way we're explaining that. But when you go to calculate, we can see that very clear here. So simple meaning the derivative tell us the instantaneously right of change. So this result means Psi x changes at a rate of cos x. Right, psi change at the rate of cos x. At every point on the psi curve, the slope of the tangent lies in given by cos x. Right. Quick reference summary. Every derivative formula is a precise answer to how fast is this function changing. But this formula here, we just recorded one there, right? That the reference, the derivative of x to the power of n equal n x n minus 1. We learned it one. We learned it by hand anyway. Why is it true? That's the algebra plus binomial expansion. The core intuition is each extra power add a layer of row. The rate of a to power x ax will do that's a limit 3 plus definition of a special number, right? A to power x row at the right required are equal to so. The real psi x equal cos x, all right? So you would limit 1 and 2 plus angle identity. Cosine is the velocity of psi. The rate of cosine equal minus psi x, right? We said limit 1, 2, and 3. Angle identity we're using that to prove it. So psi describe how cosine fall. The x on log x on 1 on x, the limit 3 but inverse the relationship. So log x grows slower, x grows bigger. So the key takeaway, derivative formula were not invented, they were discovered by carefully asking what happened as the tiny change shrinks towards zero. Every formula in the table is the answer to that question for specific kind of function. All right. We look at all the functions. Here is a useful summary of common functions involving logarithm, exponential, trigonometric function, and their derivative together with practical real-world application. Look at natural logarithm, f(x) log, so we know that derivative is 1 on x. We explained that before. In real-life application, economic diminishing return, we talk about investment diminishing return. If profit grow according to PFX, with this sort of function, then you got a derivative law that can say that 100 over x. So the rate of change 100 over x. The derivative show that each additional unit of investment produces a smaller increase in profit than the previous one, because when x increase, one reduce, increase slower. So natural logarithm, right? Natural log, right? Lower than base 10. This is base 10. Go to the other one called natural log, the one by 10. So that's very important. By 10 is a constant here. So f equal log by 10. So derivative is so 1 on x log 10 here, just only this is the constant, right? Realize after earthquake magnitude, right? Like Richter scale measure a lot. Earthquake magnitude is logarithm, like this is the formula they measure earthquake. A small increase in magnitude corresponds to a huge increase in energy release, right? Now we look at the exponential raw function with e to the power x. Derivative will be the same. Real application of population growth we use for population growth derivative here. So the population growth rate increase as the population become larger. Of course, that's proportional, right? General exponential function. This is function a to power x. Remember, this is a. This is any other constant, right? It's not a. Not the exponential, right? So the derivative will be ax log a, ax log a, right? This is we learned it too. Make sure to remember that. Real application of computer data row storage requirement often grow exponentially over time. All right. So look at exponential decay. Look at function f e to the exponential minus x here. The derivative will be minus a to minus. So real application of radioactive decay. In a radioactive decay, this is the function, and this is a derivative. That's a very popular function, right? So the derivative gives the decay rate of a radioactive material. All right, the psi function, we know that f psi from the derivative is cosine equals x. So real in the favorable motion, we saw the way before. It's a high derivative give you the high 20 plus, you get derivative. This first derivative of the function here with 15 cos t depend on. The derivative represent the vertical speed of the path or vertical speed of the path center. long. Okay, sorry, I got a power back. Okay, so what about cosine function? With a cosine function, the derivative will be minus sign. We said that before. So real life application, alternative current, AC, electricity. This application derivative, take derivative of this to give it the derivative measure how rapidly voltage changes. How voltage changes very quick, right? Tangent function, the function f equals tan x. So the derivative is sec square x. Real life application rho radian. If the rho angle is theta, so slope is tan theta. The derivative tells engineering how sensitive the slope is to changes in angle. Okay, square root function. So look at function fx square root x. So derivative will be 1 and 2 square root of x. Real life application with stopping distance. Vehicle stopping distance can be approximately by this function. K square root of velocity. The derivative shows how stopping distance changes with speed. Right? Change when you speed. If you're running fast, it'll take you long distance to stop. Okay. Reciprocal function, we talk about fx1 on x. So derivative with my equal minus 1 on x squared. All this can be proven. Right? All this can be proven. Real life application is signal strength. Signal strength often decreases approximately inversely with distance. Okay, that's a real life application. Okay. Quadratic function we done that many times in the past. Function f x squared is so derivative will be 2x. So real life application distance travel under constant acceleration. Acceleration, the derivative will be vt velocity, at acceleration. The derivative gives velocity. Okay, cubic function. We look at fx3, the cubic function. The derivative will 3. N. That means the derivative is n. We bring n3, and this power reduced by 1. 3x squared. Real life application volume over Q. V equals x cubed. Derivative become 3x squared. So show how quickly volume changes as the side length increase, how quickly the volume will change. All right, this all the functions they got all their real life application that we're learning for, and all these are derivative. I show you the program, Python program as usual. You can input any function in there, and they work out derivative for you in first order. Because this is derivative first order, can do second order, third order, fourth, and fifth order. We're gonna run 5 order, right? 5 order derivative on my Python program. Okay. Uh, General power function, we just talked about before general function like the derivative will n x n minus 1 reduced by 1. Here like engineering scaling law like R I equal R squared. So volume V R cubed and so on. The derivative help determine how rapidly the quantity rose as dimension increase. Okay, logistic law like function like fxl on 1. This is power called log, right? Logistic law. So derivative law is very complicated. You can put one into my program. They will work out, explain to you step by step to get this one out. All the function will be explained in my program. All right. Real life application with disease spread. The derivative means a measure how quickly an epidemic is growing at a particular time. All right. Now summary, the table. We went to solve all the function in list more here, and it's a corresponding derivative log x1 on x. We're using economic information theory. Log by tens, right? And then earthquake scale. We talk about that. This is popular population growth. A to power x, ix log I is data row. Here a to power minus x equals minus x, x is radioactive decay. Psi x, derivative cos x, ferric wave, we talked about cos x, derivative minus psi x. So electricity, right? Tan derivative sec squared will be rho radians. Square root, we got 1 on 2 square root x, stopping distance. 1 on x minus 1 x squared, signal strength. X squared, 2x motion physics, and x cubed, 3x squared cubic volume. X to power n, x, n minus 1, engineering scaling. So logistical derivative is population and disease modeling. We talked about before. This is only summary table. All right. So now got a three product rule. I'm going to explain you because very important rule in tech derivative. One product rule. We talk about the first one, product rule. Product rule, that means a function y is the product of the two functions, right? Function y the product of two functions of x here. So derivative start with a limitation there. I'm going to prove it, right? Prove how to get it derivative here. Observe. We just a definition of derivative of the function. We talk about limit of plus little x, right? This one plus little this function change a little bit, the input change a little bit, take away the function, divide by x, a limitation. Right? That's what we talk about. That's the main principle behind the explaining derivative. Then to simplify the number right here, add and subtract the same term shown below. If you subtract, we simplify it one and then we add one in the insert this term into the numerator, then regroup the expression so its part assembles a different quotient, right? You see that we got this part here, put in here. We take away this part. When you take away, you add it on to balance out. Take away the function in the back here, right? Calculate all divided by hex, so no change. So from here we split them. After grouping the term, take the limit I hex approach to 0. We split them to here. Fx plus this one g hex. So this is the function here, right? Approach. This one hex approach to 0. We got a limitation from this term and limitation from this term. So we get a product rule fx is this a derivative, right? This is derivative of function g. This is derivative of function f. So that's the formula. Fx times derivative of gx plus gx times derivative of fx. So therefore, the derivative of a product is the first function term, the derivative of the second, right? The first function plus the second function term, the derivative of the first. This is a formula we remember. So example, y is sine x squared sine x. Then we apply the principle there. F I will call fx is x squared, gx equals sine. Then we apply the product rule, right? So we substitute there, we got to answer straight away. Y dash equals 2x sine x plus x squared cos x. Okay? So because you know that derivative of x squared is 2x, derivative of sine is cos x, right? Just substitute in it. So product rule, all it can be, when you run my program, I'll explain to you a bit more detail than this, right? Right, now the second one, the quotient rule. Why quotient rule? Y equals fx divided by gx, right? So with gx different for is not 0, right? If gx is 0, it become undefined. So start with the definition again, how to prove it. Let the definition be plot a little x here, add a little more here, add a little more on function of x, right? See what happened. From here, we combine the function, right? We make sure we combine the fraction here, right? So give them a common denominator, right? A common denominator. So when you do a common denominator, you end up like that. From here, you expand down here, right? And you add and subtract same term, fxgi. So when you got this one here, then you take away fx, subtract fxgi. Take the one, explain, you take one out first. You can see the one from this one. You can come gx times fx here minus fx, right? Minus fx gx plus h minus gx, all divided by g h just expanded. And so we split it. We split it up together. You get the function here. Take away the function here. When you split it up, right? From here, we'll take the limit. Limit gx fx minus fx gx divided by gx squared. The bottom here, gx squared. So that's why, therefore, we end up the function derivative of f on g with f dash g minus f g dash divided by g squared. Right? This is a formula we have to remember called quotient rule. They call quotient rule. So the example is y x squared over x plus 1. For example, so we take the dash x could be substitute in the formula f dash g minus f g dash over g squared. So substitute all the number here. This is f is the top one, g in the bottom one. Right? Fx equals 2x, right? fxg minus f gx will be 1. FGX 1. So this is the answer. This is called quotient rule. Right? In my program, you want to see explained with more detail. Quotient rule. Now the last one is chain rule. Chain rule got two ways to explain this. Right? With chain rule, suppose got y got function of f of the gx. Right? That's the function of the function. So we split on u, let's u equal gx. So this function y become fu, isn't it? F and u will become variable. Instead of function become called u. So if we want dy on dx, so derivative of y with little change in x. So more the proving we will start from this one here. Same thing with plus little x in a. But the function plus little x, take away the function or divide by x. So we multiply and divide by this term. We multiply so by watching there. This is very important, critical one. So got a f this function here. I check here with time. We time this and divide by this. So it's exactly the same one, right? Just add on one on time, one divide. From this, you see, look term here. This term may look very familiar, right? F gx, right? Derivative of gx. Gx times g dash x. This derivative, right? So from here, you can see that very, very clear, right? That derivative. So therefore, derivative of a function, the function will be f equal gx. That means the derivative by on gx times the gx derivative of x. Derivative of x on g, right? So this formula you need to remember what we call a chain rule. That the first way we're using this one is to prove where the formula coming from. Right? You can go to step again, right? You can see that very clear. That's the answer. There's another way to explain it too, right? On chain rule, we gonna call intuitive proof. Very simple. Well, do it again. This one y equal f gx. We're still the same thing. U equal gx and y equal fu. Now we're gonna find du on dx, right? The derivative of y by a variable x. So a small change in x produce a small change in u, right? So delta u. Would produce a small change in y from delta u change into little change in y. So then you got delta y and delta x. You got delta y, which is on delta, just put delta u in the middle here. Delta u times delta u divided by delta u. So this one unchanged. By on this one here, this one they want to give you dy and dx. This are dy and du on du. This one du on dx. So this means the formula here give you derivative of the function y on x equal dy and du, which is this one here, and du on dx, which is on here, right? Two derivatives. See that? Derivative first and derivative here, two derivative. Right, so the same, end up the same formula, right? So look at example. We call outer function, inner function, outer function. Y equals sine x squared, for example. So fu, what that mean? Sine u, right? U equal x squared. So take derivative there, dy and dx, we got cos x squared times 2x. Yeah, so y we can apply the function f gx here, right? Times g dash x. My cos x squared với sine function of remember sine equal cos, right? Derivative of sine equal cos. And this is u dash equal 2x. So that's the answer. You want the x of the sine x squared equal 2x cos x squared. Right, that's the chain rule, three rule, very important rule, right? When you learning about derivative, you will see all that. Okay, why this rule exists? Going to explain again, right? All three rules are consequences of one idea. This is here. They all come from this idea. We said that many times. Little change in x, or the function take a function. Little change in x, the limitation when x approaching zero. So product rules come from expanding the change in the product. Right? A quotient rule comes from expanding the change in a ratio. And chain rule it comes from tracking how one variable changes through another variable. So real example like some rule that we know I look at the total cost, material cost, plus labor cost. And product rule without area changing, y angle changes. Quotient rule look at fuel consumption, like distance divided by time. Chain rule is compound growth, population growth, or radioactive decay. This is a real explanation example that we're using all the mathematics on there. Okay, now this one done on this presentation. Now, next one I want to show you is look at my Python program, right? How my Python program works and how to explain this is Python program here. This is very big one, of course, because this we got a lot of information. We're gonna roughly go through this one because this is quite a big program. Uh, you know, over about 1,478 lines, right? That's very long program. Let me run the program first. Look at the result, and we come back. All right. We run the program now. First thing, the first one program going to put you this table. I got professional derivative and analyzer, right? Got this input guide. They call input guide. The guide below show the correct format and help avoid input error. Mathematically, we call x squared, x cubed, 3x on, but meaning the variable x squared, this one, variable x cubed is all right. We all understand this straightforward sine function like correct. But when you enter in this f, right? This one got to put like it. Instead x squared, we can put x2, right? We just put x star 2. X cubed, x star cube. 3x with 3 times x. This is star here, 3 times x. 3x squared could be 3 times x squared, right? For the polynomial, the same thing. This one x squared plus 3x minus 2 put down x, this could be x squared. This is plus 3x minus 2. Sine x, you can put a sine x, right? This input here. X times sine x, put x times sine x, that's input. Because the program is structured in a way that it can read, right? The program can, computer can read all this sine here. So exponential, we put exactly the same like square root x cubed RT, x, right? This is talk about quotient, you put x squared, x squared minus x plus 1 will be like that, right? Sine x squared will be like that, right? This is x squared. Okay, so this is input. You have to make sure when you input, you this column here, the input, right? For example, a symbol the vary x is variable x squared mean x squared. That was explained before. X3 mean x3. Okay, this is the only explanation to make sure that we can input correctly. Okay, now the end of the function here. You put in any function you like. In my program here, you put in any function here, they're gonna work out for you, right? So, for example, I just give you one example. Pick any example that you want, your own function, right? I just give one example simple here. I got sine. So for example, I put sine x, right? Times cos x, for example, anything to see what's going to work out the derivative. So when put in the function, then you enter. I want to find out what's the derivative of sine x times cos x, right? I calculate the up to much with order because you can do up to 1 to 5, right? But my program, although you put enter, they end up 4 level for you. And let you specify, otherwise we run 4, okay? I specify this guy, I run 5, for example. Go. So a wrap limit, that's the way the wrap look like, just enter. You don't need to change it, right? If you want to change it, they can wrap look very different too. When you put that output very quick, once you done it, to give you the output. This is the input, right? This got you put in so they give you kind of function here, the function sine x times cos x, that's what we're asking for. First derivative give you straight away. Derivative will be cos 2x. Second derivative will be this answer. And third derivative will be this answer. All right? And you see that the fourth and the fifth derivative. Very quick. The work very quick. Computer is amazing. And all this is called special point. Special point, I mean, special point including local maximum, local minimum, right? And inflection point, right? When we remember we learned it in quadratic equation, right? Minimum, maximum, and inflection point, right? Yeah. Minimum when you are when the y value is smaller of the curve. So the processing time is 0.1295 seconds was amazing. And they do all this, draw everything for us, right? Draw all the chart is draw everything only 0.1295 seconds. We want to save figure into file because when you design this one, I design if you want to save into your file to keep the record. If you don't want it to put no, you don't decide anywhere. It put yet decide in the computer for you. Look at here. So amazing. Yeah. Look at it. This is the outcome. Look at the outcome here. So the function the reader fx how x equal x draw give you the law here. Amazing. How you work in they show fx first derivative secondary, third, fourth, and fifth, right? And these are all the local maximum inflection already provided to you for the function. Right? They tell you all the point. Further working, how to explain working. So this one will explain a bit more in detail. Like function f(x) sine times cos x. So first derivative working, that means using product rule, right? U v dash or u dash v plus u v dash. So step one, identify u and v. U, of course, u is cos x, v is sine x. So we differentiate u and v separately, right? U dash, that means cos x give you minus sine x. Sine x give you cos x. So step three, substitute in the product rule. Substitute in the product rule. So I got all this. Substitute in there. Step four, expansion is product, right? Give you the answer. Step five is final combine term by term. So the final answer will be minus x squared plus cos squared. So that this is final answer for first derivative. And after that, for this one here, when you go to first derivative minus sine square x plus, and you are learning trigonometry, they will equivalent to cos 2x, right? Equivalent to cos 2x. It can be proven as well, right? So from here, you see that it provide you all the derivative result. Now, I'll let you know, go 15 special point, 15 special point, amazing, right? Maximum, minimum, they got all answer for you. So explain fx is the slope or rate of change. Second derivative, talk about concavity. We did it before when you do a quadratic equation, when we did the parabola, right? Parabola and uh, binomial, polynomial as well. The change of acceleration and for all the advanced curve behavior, the fifth order talk about higher order curve behavior. So when your maximum minimum inflection, when the maximum where after change the sign, inflection when F2 that change sign. When you concave up, concave down, we talked about that before. Okay, so when you look at all this, computer work amazing. When you put I will try different function later on. I try one, this called production rule, right? We try different one. So once you done that, you can come back here, review your answer here, right? That's the way you work out all the function for you, right? Just the other side, just show it, just summarize it for you too. And all the point here, all the turning, all the special point, called unit special point, right? Local maximum at x equal fx how. All these are special point, okay? Maximum, local minimum, and you can see that inflection point. Okay, so if you want to run another function, you say, yes, I want to run another function here, analyze another function, yes. Now I'm going to put something very simple, enter, for example, this time I do the normal one here, simple x cube, I do x cube, x cube plus 2, plus 2 x squared, 2 times x squared minus 7, for example. They put a function like that to work out for you very quickly. How, again, the real afterward order, I'm going to do it 5 order again, maximum. Then I all this graph, just leave it like this. Keep going, x, y, keep your answer straight away. Look at the answer here. Look at your answer here. So this is the second one. Okay. We put the function x cubed plus 2x cubed minus 7. First derivative give you straight away. 3x squared plus 4x. Second derivative, third derivative constant, of course 4 will be 0, right? The derivative of a constant is 0. Same like this one. So total how many special point? I got 3. Local maximum, local minimum, and inflection point, or 3 point. Forcing times 0.046 seconds. Quick, too quick. All right. Now we look at this one here. I don't want to cite the 5 foot n in it. I don't want to cite the 5. Look at the chart. Look at the result here. Amazing. Only few less than a second. Look at it. So we put in function as to do x cubed plus 2x squared minus 7. So it's the function f, the way you draw the function f like this. First derivative end up like this, versus the rate of change coming down, and come up very quick. Okay. F2 that, F2 that, so that's the one this line here. Straight line, of course. F40, F50, and that means one straight line, right? We learned that one. Constant. So first derivative working, look at first derivative working rule apply. This one is sum or difference. Difference rule. Difference are each term separately. So step one start with a function given x cubed plus 2x squared minus 7. So step 2 will difference term by term. Derivative of minus 7, of course, 0. Derivative of x cubed, okay, 3x cubed, you get 2x squared equals 4x. The three terms we got there, put them together. So derivative of 3x squared plus 4x. So final answer. And all the negative derivative, you keep going, doing the same principle. Yet you got f2, right? But f3 will be the constant. Now f the order 4 will be 0 and flip 0, like I said before. Special point 23 point, to repeat for you. Right, I thought this one it will be the same per order because first derivative always talk about slope or rate of change. Second derivative talk concavity, curvature or concave up, concave down. We talked about before. Right, change of acceleration, right? Advanced curve behavior, higher order curve behavior. So maximum minimum is the first derivative change in sign. Inflection the f derivative change in sign. Okay. So when you close the one up, you come back to the screen again. Okay, now we're doing a different rule. We'll change different one. Again, I just ask you if do another function. Yes, you put another function. Or do another one. Now we draw product. Now we do the chain rule. I do a quotient, right? Try quotient rule. See how we gonna do. So, for example, square x square divide by something divide by x cube x anything that you want to work in, right? For your life, make sure you put right x cube right cube minus 7, for example, right? If you have own function, you put in yourself, right? Your own function. Yeah, how it work it out for you. This will be a quotient rule, I think. You see that? Afterward order, put the 5 order again. Put the 5th order, right? So the reps no change, no change. Now here your result. Well, very quick, amazing. Look at it. We just put in the function in x squared divided by x cubed minus 7. So first derivative give your answer already. Second derivative, third, fourth, fifth, very complicated, and I got the fifth derivative here. So special point, how the special point you got here? Total your special point got found 4 local, minimum, local, maximum, inflection, processing time 0.38 seconds, very fast. Okay, now look at it. So, and again, I said no, I don't want to save it. Now look at the chart, look at the result here. The quotient rule, check what's how to explain it in detail here. Oh, this is the function x squared divided by x cubed minus 7. Right, we said that's fx, otherwise you're going to draw the square, draw the chart. Right, this is the graph of fx. Red one, first degree, second degree, third, fourth, fifth. Where the local minimum, we see the local minimum, right? And local maximum, right? Local maximum, that's how to go when you go to, like you can see that. And inflection point. So first derivative working here. Look, this is the fx we got here. We just put in first we're working this quotient rule. What's quotient rule? Remember the formula? uv that's u that's v minus uv that all divided by v squared. So step 1, identify u and v. U x squared v log a. Step 2, differentiate u and v separately. Right? Differentiate it, right? Take first derivative, take derivative it. Step 3, you substitute in the quotient rule. Substitute in the quotient rule. Right, divide by x squared. You know, the quotient rule u that v minus uv that divide by squared, substitute. Then you simplify and expand it. That's what you end up here. This one you simplify and expand. You already expand and simplify, right? Done. So final answer. This is the final answer. And then you follow the rule again. You put the next derivative all this. Will give you a derivative of fifth level, or fifth order will be very long one here. Okay, so the total special point is 4, right? We said that before, local minimum, local maximum, inflection to inflection. Right, you close it out, remain, come back here. That 2 inflection point, local minimum, right? That's all. That's all our result. So you run another one, I'll get, let us do another one. Change rule, sorry, that now one. Said, yes, I can do another function. So we try everything except the chain rule. What's the chain rule look like? I just check something very simple here. X to the power 3. Chain rule, you got function or function like the two functions. X to power 3, for example. Power 3 plus 6 square to power 3 2. Right, take the derivative function of the function. Okay, this one to the power 3, sorry, to power 3, not times 3, to power 3. Okay, when you do this one here, this could be a change rule, right? This is a function fx depend on this is a change rule. Okay, try, see how we go. Again, I do 5, maximum 5, see how we go. Again, we're gonna do it very quick, the answer, very quick, it's amazing. That's what we put in here. Let me look at the result here before that. This is the function we put in. Fx x to power 3 plus 6 is 2 order to power 3. It's all to power 3. Surprised that I like there should be 9 power 3 up here. Okay, and our first derivative, we take the first derivative and the second derivative, third, fourth, fifth, give your answer very quickly. Give your special point. How many special point out here? For a 5 special point, 2 stationary flat point, inflection goes in 0.09 second. It's amazing. So step no. I don't want to save it. Look at the chart. What does the chart look like? Look at the wow, big. All right. F3 x cubed x to power 3, first derivative, this called power rule plus chain rule. Identify the outer, remember the outer power and inside function. So the outer power in this case is 3. Inside function is x cubed plus 6. So step 2 different the inside function, differentiated. So it was 3x squared. So final answer will be, you remember the chain rule, the fx 9x cubed plus 10x5 plus 2. Oh, this should have some more step here. No, I didn't show it. It should have some more steps. So make it easy to understand. Because you remember the chain rule there, they should work it out down here. Okay. When you go to my I'm going to show you how to see a bit better result in it when you're running your own computer or even on your iPhone, you can run it and you can see one explain a bit more detail than they. Okay, let me go through that one for you now. When you go to my YouTube, right? Go to my video, I show you this one. Okay, this is the next one I want to show you here. So that probably might be a bit easier. Let me see where I get the one out of here. Here. Okay. The next one I call this is my program here convert to called Streamlit. This one called Streamlit app. Right? Because Colab, Google Colab cannot run this. Because the way I design a program, Google cannot. So I find another venue. I can work out that you can use my program on your own computer, right? Your computer or even on your own mobile phone. When you click on the link, I'm gonna give you the link. When you this is the link. When you click on the link, right? This link here, you copy the link. On my video, I show you the link. It will be this one. When you click on the link, it will appear one for you. Because this will show you. I give you a comment matter. This is the input guide. So you explain in my Python set explain x squared. You got input like this, right? XQ got input like this. When you go there, you will see the one straight away. Okay. So in this program, that's why I explained already in my Python program. This was in Streamlit app, right? They got to go to I got to work the one to GitHub. From GitHub, we go to Streamlit, right? So look at here. This I give the original example. I set up in this one here. You can put any number here at your law, right? Or any function that you put in. Okay. In this problem, if original function will be a different one, I put in x squared divided by 2 x plus 1. This is quotient rule. This will be quotient rule, right? So I put on in, I enter. Anything that you put in, you enter. And then from here, you click Analyze. When you click Analyze, going to give you the result. Okay. Click Analyze. You see that started running here. Let's click you're going to run. Already run quick. They already got the answer here. Look at this. Very quick. Recognize function. X squared divided 2x plus 1, right? We put in the x squared divided by 2x plus 1. So exact Python that the way put in here. So see the result. Amazing. So quick. Running so fast. You look at the graph. Look at the graph. We said a bit. I saw all this here. F all this, and look at the derivative working out. A working function here. A little more detail on this one. This one talking about quotient rule. All right, the quotient rule we'll explain later on too. the v square. So what your first derivative u v, take first derivative and then you substitute in the quotient rule, right? After that, then you simply explain it. The final answer here. When you follow the same rule, you got the level 2, 3, 4, 5. A special point file, we already got a total special point, the two, total special two, one the maximum, one local. No inflection point here. Okay. So when look at it, I should look at it a bit more because this one too small for you to read. This one will be better. If you click on this one, first the really working, click on here, show you step by step very clear here. Right, function given here. Right, first the really working. First the really working here, we use quotient rule. This is the quotient rule. Step one, you identify U and V. Step two, differentiate U and V separately. Step three, you substitute in the quotient rule, right? And then therefore you simplify or you explain whatever, right? Then you got final answer, right? Just so first, I just only detail how to do a first derivative, and then you look at the table outcome for you. This one, he click on table and show you the result 1, 2, 3, 4, right? Because I pick this one, we pick only 4. If you move it, pick to 5, whatever you like, right? So this 4 because this default is 4. So that's your answer is all this one here, system friendly result, right? Python result, that means the power, you know, Python read that, but the way we're reading normally human read is the formula. So this is local maximum, local minimum. Okay. So this is what change streamline. This is dependent. I'll just explain to you how. All the one here because I run on Python. I using Python. When put a stream, I got a change in there. Got to import the one different one changing because something that in that input in Streamlit, you got your st tag, st slider, st number. You can see in this program here. But in my program, in my Python, you won't see all that. This only apply for Streamlit when I convert the program into Streamlit, right? Otherwise, in Python, you input, print, plot result. Remember, we do all the in normal for a long time and pair PLT show. Right? Let's see. Talk about script, right? Program script. So in this, so I'm gonna do if I want to do another one, just change the number here. Whether another program put in some side equals do something like put a sine inside x square. What is sine x square? Cos x, for example. Just I just put an example here, right? You can put any number that you want. When you put in there, then you press enter. See, press enter to apply. You press enter, right? Press enter, you give you exact table this straight away. Then from here, put analyzing. This one 4, either on the fifth 5, you can move it on to 5, right? And for 5 level, right? Default is 4 or 5. From here, you put analyze, and give the result very good. See the guy kind of working hard for you. See that? Running hard, you're going to see the result. Well, will be longer. You see that like running non-stop. So this one be a bit longer. But this one a bit harder too, because you see that this will be sine x square times cos x, so that's quite big here, maybe. Look at what's an outcome. That's it. Input value type here. That's what we got here. Ooh. This is the answer. Explaining where you get the first derivative from. This one a bit hard to read, so clicking here will be easier to see here, right? Click on here. First derivative working. You see that? X squared times cosine x, sine x squared times cosine x, first derivative working. Product rule, u dash v plus uv dash. So step one, identify u and v. U is cos x, v sine x, right? Step two, differentiate u, v separately, right? Do all this. Derivative of cos minus x, sine x. Derivative sine x is the 2x cos x squared, right? So substitute into the product rule, you got what you got here. From there, step four, expand this product. Codify, combine term like term, get this, and final answer. Give you final answer. All right. So this now you click on see different on see the table. If your table, click the table, you derivative first, seventh, fifth level. That's all the answer. That is all the answer. Five, all the derivative, all the special point you got down here, right? If, all the special point you got here. It's amazing, you know, seeing how quickly the computer work. They draw very fast and everything done quick. All right. So I think we got I think that long enough now. I think stop here. You can put any function, whatever you do, just put in here. You got your own function, put in. In fact, I should put another one exe. So I just draw another one for you. Just put another function called, because we haven't drawn ex yet, right? The function of is e ex. We put exp. Don't forget. You see that exp, right? X. All right. And this one can term another function. So you want to get x squared, for example. Just put example here. See what's going to look like, right? The exponential function.
Hey, I found this on the web for what's going to look like. Check it out.
Enter. When you enter, you always see the table input limit. So what I'm going to run analyze. Click analyze. It just start to run. Result very quick. It was very quick. Look at here. The function put in x squared times ax, right? We put in here x squared times ax. That's correct. That's the way Python reads here. That's the wrap end up here. So f function, first derivative, second derivative, third, fourth, fifth. You can see that the way and line up like that, right? So keep your hand here. You got special point here. You got all four special point, right? When you look at derivative here, very easy to read from here. So first derivative function, first derivative working. This is product. They call product rule. U that v was u that step one, and if u x squared v ax. So you differentiate them. X squared got 2x, ax is no change, will be ax here. Step 3, substitute into the product rule, right? And then you expand this product that we got, then you combine like term, right? Then the final answer. Okay, so the second derivative, you just keep going, all right? And then I look at the table outcome here. This is a table outcome. You can see correctly 1, 2, 3, 4, 5. We select file order here, so that's the answer here. 1, 2, 3, 4, 5. Very quick, isn't it? With a special bond, 4 special bond, right? X and give you Y. Okay, I think right. Now I just briefly show you about the Python script, right? It's a very long Python script, but in fact, in real life, there will be a lot of things longer than this, right? This is normally it's importing, we are importing all these packages in Python. I will learn so far, right? You can copy the script, whatever you like, play with that in your computer. Feel free to do so. But it's quite long. I just show you briefly so you can see that when you do we've got import a lot of packages, and from there we work out all the data configuration. Just go how to work out based on mathematics. This is a plot, how to plot appear and what it look like, the figure how high, how they flow and so on. This is when you draw the graph. Okay, when you draw the graph, what is the color? We're using color for them. And this one is human readable. When you got all the one, so or x squared, so when you can read it, we convert this one here. This function called human readable math format, right? To convert it in program. When you put in Python, the F, so we can convert it. Readable derivative, you do derivative. Okay, all the go there how to explaining when you bring out the title first, second, third, fourth, fifth. You remember when I show you the table, right? That derivative order, and you gotta first teaching step how to explain your first when you do derivative how to do first step by step. You remember when we talk about different rule, said all they been written in the program, right? Got different rule, and you got product rule. Got this one called product rule, and then you got to a lot, and got the next one. Keep going. Got change rule. It's gonna work out rule, how to work out all this little one here, got how to work out a power rule here. And when you simplify it, a simple rule, common simple rule, or it's something we remember, we learn all by heart, all this one here. We explained it before on the table. First derivative, and this is the guide, the way we explain the guide, put out the input guide, this is all the guide. When you input guide, make sure you don't have input error, that's it right there. And this is the banner, we put out in banner, see explain down the bottom of the guide, in the power of the guide, or the power of the guide there. And now they normalize input, what you answer like, when you input like this, they convert it in for you. Now what I did, that means they know the time, right? That's all it is. That way the way compare the read. So normal function map or sine exponential, all is how you use this, right? This is power function. You see a lot of functions they normalize how to get a result. You problem function when you put input, how you put input in. Remember when you put a fx, how you put fx in. Okay, if you put it wrongly, they go tell you that is incorrect. I didn't try that one, but I show you. When you put a wrong input in, it will tell you. When you finish, put a quick exit when you finish. When you don't want to do anymore, say goodbye for you. Yeah, from input, input here, how to put in. And then you do, now you look at our derivative down here, very complicated too, right? All the derivative I do. Evaluation, how the evaluation function. How they return the output. Validate the root number, because when you input root, then they're going to work out the function, work out all the root for you. Right, when you input root and so on. This one here, keep when you see that back on your final, when you got some, you've got indefinite or so on, they all work in there for you. Cluster, symbolic root, validation, duplicate, symbol side, triple return side. Right, all these one exception, run none. Then I got set all the special point, list all the special point. Right, how the special point you got, okay. I don't list it for you because this is the original function that the default function, right? Just explain to you that default function. All this on you starting from there, you find special point, how they work out, right? And then all this explanation. Derivative first one, second one, so critical, and all this local, where local makes sure there's a red, green, magenta, yellow, cyan, all different color, right? Well, format summary to then out, critical point, smack it, compute center y as a limit using percentile, specify inclusion, the power of program audit. Marker is all the point we said that before, slope all this explanation. That's a show you explanation on the chart. Plotting result, how we show how you show a graph, right? How show the graph, because we said that was -6 at the default number, right? You can change it when you put input there, but the default is -6. So the chart can look balanced, right? And I said, you see that this is when you add a marker in. So you can see a set function derivative. So when you look at the view line, first, second, they gotta work on it. Okay, exceptional. So last one I call analyzer, very important analyzer. All these function analyzers, analyze the data. Then the interactive session loop. When you input, you ask them yes or no. How what all you want to put on, interactive 1 to 5, maybe 1, 2, 3, 4, it's up to you, right? This input, where you want to select what way you want to go. Okay, so we say Google Pass, we say to your computer, or so computer you want to, that's why you say want to save it and not answer yes or no. If you say yes, and then go sign your computer, and then you continue to work on it, right? Yeah. Let's say entry point. Now this is a final point. When you run Python program, this is the main function. Okay, now that's the end of quite long one. Take me a long time to do it too. Right? So this is quite a bit complicated, but very useful tool when you want to work on derivative, right? When you input any number, difficult, you can work out the answer very quickly. All right, thank you for your time. See you next time. Bye. Right. Now I just briefly show you about the Python script, right? It's a very long Python script, but in fact, in real life, there will be a lot thing longer than this, right? This is normal. This is importing. We are importing all these packages in Python. I will learn so far. Right, you can copy the script, whatever you like, play with that in your computer. Feel free to do so. But it's quite long. I just show you briefly so you can see that when you do we've got import a lot of packages, and from there we work out all the data configuration. Just go how to work out based on mathematics. This is a plot how to plot appear and what it look like. The figure how high, how they flow and so on. This is when you draw the graph. Okay, when you draw the graph, what is the color? We're using color for them. And this one is human readable. When you got all the one, so or x squared, so when you can read it, we convert this one here. This function called human readable math format, right? To convert it in program. When you put in Python, the F, so we can convert it. Readable derivative, you do derivative. Okay, all the go there how to explaining when you bring out the title first, second, third, fourth, fifth. You remember when I show you the table, right? That derivative order, and you got a first teaching step how to explain your first when you do derivative how to do first step by step. You remember when we talk about different rule, said all they been written in the program, right? Got different rule, and you got product rule. Got this one called product rule, and then you got to a lot. Then got the next one keep going. Got change rule. It's gonna work out rule how to work out all this little one here. Got how to work out a power rule here, and when you simplify it as simple rule, common simple rule, or it's something we remember, we learn up all by heart or this one here. We explained it before on the table. First derivative, and this is the guide, the way we explain the guide. Put out the input guide, this is all the guide. When you input guide, make sure you don't have input error. That's it right there. And this is the banner. We put out in banner, see explain down the bottom of the guide, in the powder guide. Right, or the powder guide there. And now they normalize input what you answer like when you input like this, they convert it in for you. Now what I did that means they know the time, right? That's all it is. That way the way compare the read. So normal the function map or sine exponential or is how you use this. Right? This is power function. You see a lot of functions they normalize how to get a result. You POM function when you put input, how you put input in, remember? When you put a fx, how you put fx in. Okay, if you put it wrongly, they go tell you that is incorrect. I didn't try that one, but should I show you? When you put a wrong input in, go tell you. When you finish, put a quick exit when you finish. When you don't want to do anymore, say goodbye for you. Yeah, from input here, how to put in. And then you do now you look at our derivative down here, very complicated too, right? All the derivative I do. Evaluation, how the evaluation function, uh, how they return the output, validate the root number, because when you input root, then they're going to work out the function, work out all the root for you. Right? When you input root and so on, this one here, keep you see that back when you final, when you got some, you've got indefinite or so on, they all work in there for you. Cluster, symbolic root, validation duplicate, symbol size, triple return size. Right, all these one exception, run none. Then I got set all the special point, list all the special point. Right, how the special point you got, okay. I don't list it for you because this is the original function that that's the default function, right? Just explain to you that default function. All this on you starting from there, you find special point, how they work out, right? And then all this explanation. Derivative first one, second one, one so critical, and all this local, where local makes sure there's a red, green, magenta, yellow, cyan, all different color, right? Well, format summary to then out, critical point, smack it, compute central y as a limit using percentile, specify inclusion, the part of program of it. Marker is all the point we said that before. Slope all this explanation. That's a show you explanation on the chart. Plotting result. How we show the graph, right? How we show the graph because we said that was minus 6 that's the default number, right? You can change it when you put input there, but the default is minus 6. So the chart can look balanced, right? And I said you see that this is equal when you add a marker in. So you can see a set function derivative. So when you look at the derivative line, first, second, they gotta work on it. Okay, exceptional. So last one I call analyzer, very important analyzer. All these function analyzers, analyze the data. Then the interactive session loop. When you input, you ask them yes or no. How what all you want to put on, interactive 1 to 5, make 1, 2, 3, 4, it's up to you, right? All this input, where you want to select what way you want to go. Okay, so we say Google Pass, we say to your computer or so computer you want to, that's why you say want to save it or not, answer yes or no. If you say yes, then it goes on your computer and then you continue to work on it, right? Yeah. Let's say this is entry point. Now this is a final point. When you run Python program, this in the main function. Okay, now that's the end of quite long one. Took me a long time to do it too. Right? So this is quite a bit complicated, but very useful too when you want to work on derivative, right? When you input any number, difficult, you can work out the answer very quickly. All right, thank you for your time. See you next time. Bye.